Hello everyone, and welcome to this afternoon invited talk, and thanks to the organizers for having me and inviting me. It's unfortunate that we have to do this remote, but I will hope to keep your attention throughout this recording. This talk is about bootstrapping natural language processing for under-resourced languages, and I will specifically focus on the case of Finnish because this is something I have worked on personally myself. Just as a little recap of who I am and why I am talking to you on these topics. So I'm Philip Ginter, an associate professor in natural language processing at the Turku NLP Research Group, University of Turku in Finland, and I'm also involved in some private companies with a pretty small percentage, though. These companies are related to AI, machine learning, and natural language processing, and what I'm getting out of these companies is that I'm trying to get their understanding of what NLP looks like in the wild, kind of outside of the university. In the 20 or so years I have spent in this field, I have had the time and opportunity to do a lot of different research projects. I started with information extraction and text mining in the biomedical domain, and then I sort of worked my way into the Turku dependency tree bank and kind of general Finnish natural language processing. And ever since about 2010 or so, I have spent a lot of time just building up the necessary NLP resources for Finnish. And this is some of the lessons that I have learned during these 10 or so years I would like to share with you now. So in this talk I would like to sort of re-walk the path that we walked to bring Finnish out of obscurity onto the NLP map, and look at the most typical use of the resources that we built and relate them to the current deep learning methodology, and maybe share some experiences of what we have seen during these years. Finnish NLP, when I started to get interested in it, that's around 2008, looked quite different than what it looks like now. Practically nothing was freely available. You couldn't really process Finnish with free open source tools at any level. There was a handful of commercial solutions that have been locked up behind licensing, and there were maybe some first signs of Finnish finite state morphology open source implementation. So that would be implementations of tools that can analyze the sort of complex inflection that Finnish words undergo. And we sort of thought back then with my colleagues here that any language should have these kind of elementary resources available. And so many of what we have now just was not there, and we had to build it up. In 2021, so now the situation is quite different. Many of the basic tasks and resources are fully covered. Accuracy-wise, we are quite comparable to the big languages like English, and most of the basic NLP tasks needed in the industry are supported, and all of the necessary tools and resources are openly available. This is something I would like to stress throughout the talk, that whatever we build, we always put a lot of effort into making it openly available and not a victim to various licensing issues. I will start the talk with a topic about the Finnish dependency parser. This is something we have ourselves started with, and towards the end of the talk, I will maybe relate it to what is the current needs in NLP and maybe point out that building a full syntactic parser would not be something that I would start with nowadays, given the present technology. So what a parser does is that it analyzes text as you feed the text into it. The output of the parser is these relations between the words. So which word is a determiner of which, what is the main verb, what is the subject, and so on. And this tree, because these relations, as you see here, actually form a tree on top of the sentence, encodes also a fair amount of meaning, because changes in meaning in the sentence are actually reflected in the relations between the words. So a successful parser needs to understand a lot of the language to be able to sort of resolve the ambiguities in the language. And if we look at the output of the parser in here, the specific task that the parser needs to do for Finnish, and maybe which is not so critical for English, is also sort of morphological analysis. So I know that you don't understand Finnish, but if you look at, this is the text of the sentence, and this in here are the base forms. You will notice that just about every word actually changes between the word as it is in the sentence and its base form. So if you want to do something like search, just search for words, it's not enough that you search for any kind of string, because these words inflect and they will look different depending on in which case, number, and so on they are. And that is encoded in the parser output by a pretty complicated list of morphosyntactic tags that basically tell you just how the word is formed from its base form. It's quite important to realize that, especially at the time when we were building this, much of NLP was developed on English, and English doesn't have these problems. English doesn't have this complicated morphology the way Finnish and many other languages have. So many of the sort of ready-made tools that would work in a way language independent wouldn't anyway apply to our language of interest, and I think that would be the case for many other languages. So in order to, we sort of realized that, okay, maybe the first step to start with is to build something that can do this kind of elementary text analysis, chop the text into segments, find segments of words and sentences, and do some basic analysis of these words and the syntax and the meaning of the sentence to a degree. We took very quickly the path of actually going the machine learning way. So we thought like, okay, we have to build a tree bank, which is simply a collection of sentences that are annotated in the way I've shown in here. So basically a collection of enough many sentences that are given by hand this kind of annotation, so that we can then train a parser in a sort of machine learning way, sort of supervised machine learning. So this is what we started building. We just sampled text from various sources. There was about 10 sources that we used, Wikipedia and student magazines, blogs, and so on. And we actually put a lot of effort into ensuring that every piece of text that we include in this tree bank is having its licensing issues resolved. There is a clear license under which we are actually free to release the text later on. This is something that one should be very, very careful about, not to produce annotation that cannot be then, or annotation on texts that cannot then be released without getting phone calls from some publishing companies and so on. So we started to build this tree bank. We simply had people, or we kind of did it mostly ourselves, where we just started to build this annotation. We tried to do as good a job as possible. Every sentence was actually annotated twice so that we can make sure that kind of simple misclick errors are removed, because we then always put these two versions together and resolved any differences. And we found that a human annotator, even when relatively well trained, can do this task at about 90 to 93% accuracy. The metric here is referred to LAS, that's labeled attachment score, and that basically tells you the proportion of the relations in the tree that you have seen that are correct. So how does the parser do then? As you see, we have taken the sort of machine learning approach. So we have built the data. Once the data was built, we haven't really touched it all that much, and we focused on getting better and better and better parsers, i.e. algorithms that can learn by or that can learn from the annotated tree bank to replicate the kind of annotation that they see, i.e. parse the sentences. In 2011, the initial numbers we got were not that good. They were below 80. Remember that a human is somewhere at around 90 to 93, around there. And the initial numbers we got were 77. But a little bit later, 2013, we were already at 82. 2018, when the notion of word embeddings came, we made it to 89. In 2021, when we have all of the deep learning machinery you can think of, then we are actually at 94. And that is already very much where the humans are. I don't want to say that this is better than human, but well, the number is higher. But of course, a human can do this task on just about any text. The parser can get this number on sort of clean text that is roughly within the domain on which it was trained. But as you see, I mean, the numbers, without actually changing the data all that much, have changed from or have risen very substantially over the about 10 or so years that we have had this tree bank. And it was really the deep learning that has recently come, and a particular model, Finbert, that I will talk about later, that has made this change possible. There are other tasks that the parser needs to do. It needs to segment the text into tokens, decide about the part of speech tags, i.e. what is a noun, what is a verb, and so on. And most importantly, as you will see, it also needs to produce these base forms. And as you see, all of these kind of individual tasks, which are actually in terms of practical text processing the most important ones, the parser runs in the mid to high 90s. So it's actually very accurate output that you get out of it. And we have of course trained the parser on other languages, not just Finnish, and it actually does quite well. So we have seen some first ranks in several shared tasks. As a matter of interest, one of the most, or a task that has always been assumed to be extremely resource consuming, is to do the lemmatization, i.e. finding out the base forms from inflected words. And traditionally this is something you would do by producing large dictionaries that would encode the sort of inflection patterns of different words. That has two disadvantages. One of them is that you actually have to do it, and that is a lot of work. And another is that if you happen to have a typo in the word, or it's some new form that somebody sort of invents, then you do not get any analysis because you have never seen that word. So we have approached this through just pure machine learning and have built a kind of character-to-character, sequence-to-sequence deep learning model that's modeled upon machine translation systems that kind of do the same thing. And this model sort of just rewrites the inflected form and the tags into the base form, and it's just a sort of single monolithical neural network to do that, and that works surprisingly well. The typical use of the parser is as elementary text processing component in Finnish industry. So I have seen it be used for text segmentation and lemmatization primarily. So you need to feed into it a bunch of raw text, and then you want this text to be segmented into words and lemmatized. That's especially needed for information retrieval of various kinds, as I have mentioned previously. The dependency trees, on the other hand, are quite rarely used in actual applications, and because that has been sort of replaced by the deep learning methodology in feature generation. So the dependency trees themselves, which was actually the hardest thing to build, are comparatively little used in the end nowadays, and it was much more at the beginning. I have seen the parser in the hospitals. I have seen it in various government organizations, in various textual content management companies that maintain web pages with various search functionalities. I have seen it at universities, both for NLP and linguistics research. What we have learned about the parser is that we needed to start by making a high quality tree bank. We have really put a lot of effort in getting good data because we knew that this data will need to be created only once, and thereafter we can simply keep building the models and the parsers. We have made sure that the underlying text material is free for use, and we can release the tree bank for general use by anybody. And we have also kind of resisted the urge to model every single little peculiarity of the Finnish language. Rather, we have simply subscribed to the Stanford dependencies, which is a sort of annotation scheme that tells you kind of what these trees should look like and what are the possible relations that can be taken between the words. And we have simply applied that to Finnish. We didn't feel that that's too much of a price to pay, that we cannot model some of the small peculiarities of Finnish. And sort of the parsing technology itself has changed under our hands over the past 10 years, and the numbers just sort of by algorithmic development went from low 80s or maybe high 70s to mid 90s without changing the data all that much. And out of actually creating this tree bank, vast majority of the time went to the actual syntactic tree annotation. Comparatively less of time was needed to build the morphological annotation, because that's a relatively fast task, and we also had some tools that we could bootstrap ourselves with. And that's important to know, because the importance of the syntactic parsers has kind of diminished with deep learning. They are no longer much used for feature generation. So it might be possible to build the kind of basic text processing pipeline much faster by simply initially skipping the syntactic analysis step. And I cannot stress enough how important it is to make sure that all of the licensing is okay, and you are building on top of text that you are actually allowed to use, and nobody will be prevented from using the parser. We have made especially sure that we do not have, for example, non-commercial clause in the licensing of the parser. Now, when we have the parser, we were thinking in 2012. So what do you do with a parser? You should use the parser to parse something. You should parse some text with it, because, well, that's why you made it. So then we started to think that, okay, we have to gather some language data, and scraping the internet seemed like the only realistic option. As you know, there are some resources that kind of scrape the internet for clean, pure textual data. In 2012, Common Crawl was pretty much the only one we were able to use, but that has been highly English centric, and to some degree still is, but much lesser degree. And since we wanted a lot of Finnish text, then we simply launched our own crawl initiative, which was relatively intense task. It's not completely trivial to start crawling the internet for a lot of textual documents, but if you want to have a lot of data for your language, this is something you will probably end up doing. We put a lot of effort into cleaning and deduplication, so that the result was as good as we could get it. And we ended up with something like 8 billion words worth of data. That was what we felt relatively clean and in a sort of good shape. We parsed and reparsed this as new versions of the parser came up, but initially this data was used mostly for linguistic research and as a target for developing tools for processing large billion-word data collections, because we thought that's sort of quite exciting, because we are still computer scientists, so we like to develop kind of lean tools for processing large collections of data. Luckily for us, when few years ago the deep learning methodology hit, as many of you know, nowadays NLP is based on large language models, and these large language models are trained on large textual collections, and good data in, good model out, bad data in, bad model out is a principle that holds in here. So we were lucky to have this big collection of clean text when the need arose to build large language models and sort of bring the Finnish NLP into the deep learning age, if you will. So this work on building the parse bank maybe was not so useful from the parsing perspective, although we have of course done a lot of work on that as well, and a lot of research. But most importantly, we gained a large collection of text that we were then able to use to build the deep learning based methodology. So far we have sort of built a pretty good parser for Finnish, and we have gathered a lot of running text by crawling the internet and then cleaning it up, and that sort of naturally brings us to much more recent topics. This is something that we have done in the past about 2 years, and that is of course reacting to the fact that much of NLP has now moved into deep learning methodology, and the deep learning methodology works on large pre-trained language models. So without going too much detail, everyone now is using these transformer-based language models, which are trained on billions of words of text. And the way this works is that you pre-train the language model by sort of exposing it to large collection of text, and then you use this pre-trained model as a basis in subsequent applications. So you take this massive language model and then you build on top of it already a relatively thin layer which carries out whatever task you are having. Is it parsing or is it classification? So for this to happen, you sort of need the raw text. This is something we have built in the previous part, and you need to kind of train the model yourself. Now, why is that? Many of you might be aware that in addition to, or when BERT was released, then it was released as an English model, and in addition there was released also a multilingual model that was trained on 104 languages, including Finnish. It was trained on Wikipedias for these different languages. And that sounded like a great idea, because you actually got this model already pre-trained by Google for your own language. And we thought that, okay, well, great, we don't have to train our own BERT model. We can simply use the multilingual model to do our NLP. We have very quickly started to realize that that's probably not the case. So if you look at this chart, we sort of started to probe the model a little bit, and we started to test it with various tasks, and the picture usually looked like this. So if you have this English BERT model, which is sort of monolingual, the model has seen only one language, so you would get something like 90, for example, for this particular task. And if you look at the multilingual model, you will see a massive drop. And if you look at Finnish, you see this like extreme drop. So you see that the Finnish numbers are really bad compared to English numbers, and that sort of tells us that the multilingual model is not that good on Finnish, and I would not expect it to be very good on many other languages. That's not to sort of badmouth the model. I think it's fantastic thing that someone has released a model of this kind. But we have realized that, okay, we have to actually build our own if we want to have as good numbers as you would get for English. And this is what we have done, using the fact that in Finland we have this one compute center that we can all use, and that has rather substantial resources that we can sort of dip into. This is not something everybody has, regardless of where they live. This is just something that we happen to have in Finland and can be using. So in around 2019 we actually trained this model. Back then, I mean, nowadays a lot of people train these models, but back then it was one of the very first monolingual models that did not originate in Google. And we have done a lot of kind of heavy-handed filtering on the data. So we have filtered, for example, this web crawl data of ours from 8 billion words to 1 billion words. We have thrown most of it away and kept only the stuff that we thought is like as clean as possible. So again, thinking that, well, since this is what the language model will see, this is what it will learn, it should not be looking at some random noise. So we have put a lot of effort into the filtering, and after that we sort of pressed enter on the code and trained the model. That was of course not quite the whole story. What happened in reality is that we have spent a lot of effort debugging various issues and basically getting everything to run. Again, this would be a bit easier nowadays than it was 2 years ago, because some of the libraries have matured. But in the end, a single run, the final run that basically gave us the model, was running for 12 days on 8 GPUs. In reality, I think the resources that we have spent were about 10 times that, because we need to start and restart and restart and restart. But it has paid off. I will show you now few example tasks where we have tested the model. The first one is named entity recognition. So, given a text, you have to recognize the names of people, places, organizations, and so on. Now, this in here is what was the state of the art before. This is what you can get with multilingual BERT, and the blue one is what you can get with this monolingual Finnish BERT. And you see that the difference is rather substantial. The numbers have gone somewhat up since this figure was produced, but you see the story is quite clear. I mean, the gain by the model removes most of the difference between what we had and human performance. For dependency parsing, the story is again the same. Most of the gap between where the model was and human performance has been closed, and again this has gotten better since this figure was produced. So we are much closer to human performance still. In text classification, same story. This was a particular task I will not have the time to talk about, but this is what you would have before with just basic technology, and this is what you would get with this monolingual FinBERT model. So this axis in here is amount of training data, and this axis in here is the accuracy of the resulting model. You see that especially if you don't have much of annotated data, the difference here is striking. You could have, with some basic tools that we had before, you could have about 50%, including the multilingual BERT, and with our own, you can get numbers that are 25 points better. So this kind of shows the power of the model. So what we have found is that just relying on the multilingual model is not enough. It's maybe tempting, but it's not enough. And the FinBERT model improves the state of the art on pretty much all of the tasks that we have tried. The results are within few points of human performance on many of tasks that actually matter to us. So there is more. We have because once you train one of these models, then you can just start repeating that exercise for many other languages. So we have trained 42 monolingual models on Wikipedia, and we are quite happy to sort of collaborate on training models for more languages, sort of putting the resources we happen to have available here to us to good use. Here we can see the sort of effect of monolingual versus multilingual across a lot of languages. The kind of zero line is here, and anything that's above is better for the monolingual Wikipedia language models, even though they were actually quite small, because we had to cut some corners to be able to train 42 of them. This one time I was quite happy to see that Finnish benefits most. Usually Finnish had the worst results for everything across the past 30 years or so. So what we have learned is that, and I hope you are convinced having seen these numbers, having a good monolingual model is a real enabling resource for much of state-of-the-art NLP. As far as the data, a large text corpus is needed, preferably in the billions of words region. This corpus must be of very good quality, and any effort spent here will pay itself back. You also need to have some compute, so you need to have GPU time to be able to train these resources, and in case you don't have it, then there is a large community out there, and finding ways to collaborate on that might be quite possible. We have trained BERT models for other languages as well. So as the third topic, now now that we sort of worked our way towards having the basic language model, we realized that we are missing one critical resource for Finnish. That I think it's quite amazing that the named entity recognition, which is a task which you have seen a while ago. So given a text, you have to recognize names of things, people, places, organizations, and so on in it. So this actually did not exist for Finnish until as late as 2019. I think that's quite amazing because it's one of the very elementary tasks in natural language processing, which is much needed in a lot of applications. And there was a dataset released by our colleagues in Helsinki in 2019, and for sort of copyright reasons, it was produced on Finnish Technology News as data source. And it was shown in their paper that, well, if you apply a model that's trained on Finnish Technology News, you will it will sort of break down on Wikipedia, which is quite different looking but still very relevant text source. So we realized you need a more varied Finnish NER corpus and set out to produce it. We have taken the tree bank that we had because it covers a lot of the domains that we care about. It has Wikipedia, it has blogs, it has you name it. We probably have a small sample of it in the tree bank, and then we started just annotating. It's not a particularly difficult task. So when you want to do this kind of NER annotation, basically all you need to do is just select the segments with your mouse and then pick labels for them. So what is a location, what is a date, what is a person, and so on. And a semi-skilled annotator can actually go through a lot of data in a surprisingly short time when building a resource like this. So when we were all done, here is just something that I want to show you, is that if you pick the preview state of the art, you get something like 74% F-score, and when you sort of lift it to this data set that we have produced and the FinBERT model, you get to 91. So that's a rather substantial change in accuracy that we have gotten by simply getting good representative data and feeding it through kind of good language model. Again, we were not trying to come up with something radically new ourselves. We just relied on sort of ready-made lists of entity types that should be annotated in ontonodes, and then we have just picked these and just annotated them on the text that we had. We have used a lot of students, so this NER project was actually started as a student project in one of our courses. And the students built the first round of annotation in a span of several months, not years, months. And then we have had some focused effort thereafter to clean and publish the data, to sort of resolve any noise that seemed to be present in the data and actually publish it. We have also built on top of the tree bank that we already had, because the syntactic information was quite a useful starting point. So what have we learned? Named entity recognition, just being able to point in the text names of people and places, is an extremely useful useful resource to have. It has numerous downstream applications. I have seen it used a lot, and it's a comparatively small effort. All you need is to go through text and mark these entities up. So if there is one resource to start after you have sort of raw, clean text data and the BERT model, it's actually the NER, because this probably will give you the greatest mileage for your investment. I think it's time to conclude. Have been talking for 40 minutes now. I hope I still have your attention. So there are other data sets and other tools that we have been working on, especially recently, but I just didn't have the time to cover all of them. But as you see that the classical tasks around morphosyntactic parsing and tagging and lemmatization are actually very close to human performance from an engineering point of view, even for a language that's generally perceived as somewhat difficult, and that's Finnish. The deep learning and the BERT model has changed the game enormously during the past year or so, and maybe two, and so this is where one would kind of need to start. This is what one needs to get good numbers and sort of accurate enough systems to deploy. We have a lot of upcoming resources on tasks that go deeper into natural language understanding. What is important here is that all datasets and resources that we have created for Finnish are actually fully open and usable by anybody. We have been very, very careful about the licensing in here. And as you have probably understood, you cannot expect anyone to produce this data on your behalf. So if you want to get NLP for some language, actually starting with getting good data is paramount in importance. Out of what I have shown you, the syntactic annotation of the tree bank was by far the most resource intensive project. If you were to drop the syntax and just keep the sort of basic segmentation and tagging, you could probably get away with considerably less of effort. The critical step for us, even though we didn't know it at the time, was gathering a large corpus of clean, just plain textual data that can then be used to build the large language models on top of which you can build the rest of NLP. A lot of the useful resources, NER, sentiment, which I didn't have time to talk about, the basic text processing, these are actually not especially time consuming to build once you have the textual resources to build on. I mean, sometimes you can get there in just few months and few people, and then you have it. And in terms of computational resources, pre-training these large language models is the heaviest thing that you will need to do, and one can always strike some collaboration in case that you just don't have access to these resources. I would like to end with some acknowledgements. So thanks for the organizers for inviting me, and the acknowledgements here go of course to the whole Turku NLP group, and especially Veronica, Sampo and Jenna, who have contributed also very concretely to these slides. So thank you, and I will be happy to take any questions.